Thank you for joining us for our webinar today. We're just delighted to have this session with you. And we first got to know Vamsi and Bala. They are the architect and senior data engineer from Disney plus Hotstar. And if you don't know Hotstar, it's actually the fastest growing division, fastest growing branch of the Disney plus umbrella. So very exciting. We first got to know them at our Scylla Summit back in January, and we tried to get them to cram all that they're doing into just a 10-minute session. And it wasn't nearly enough time. So we're very happy to have them back here today so that they can share in full detail their use case, their requirements, how and why they migrated to Scylla Cloud. Again, that's our database as a service. And most importantly, the lessons that they learned along the way. So they're going to share their experiences with you. But before they do, as I mentioned earlier, we're going to have a question. I'd like to launch that now. We'd like to ask you about your experiences with NoSQL. And I don't see the poll question. There it is. So what's your experience with NoSQL? Are you new to NoSQL? Have you used other NoSQL databases, but not a Cassandra query language or CQL database? So perhaps you're using MongoDB. Have you used Cassandra or another CQL database? Or have you used Scylla? And we have both CQL and DynamoDB API modes. So I'll give just a couple of more seconds. Please give us this information. It helps us to understand the audience. And again, we'll share the results with all the attendees after the webinar. Okay, great. Thank you for that. Let's close the poll. And without any further ado, I'm happy to introduce our first speaker. It's Bala from Disney plus Hotstar. He'll be followed by Vamsi, the architect there. And Bala, I'll hand it over to you to share your video and take it away.
Hey everyone, this is Bala from Disney plus Hotstar. Today I'm going to talk about the use cases which we use at use the Scylla Cloud for our Disney plus Hotstar platform. Disney plus Hotstar, as Bob says, we are a largest streaming service platform in India. We use a bunch of movies and TV shows across India and all kind of regions and all kind of languages. The users come to the platform to watch any movie in their own language and TV shows which they prefer to watch at any point of time. A completely on-demand service hosted. We host almost like 300 million active users every month. And we also recorded a concurrent viewership record at one of our World Cup matches. India is the biggest cricket watching country, and we recorded 25.3 million concurrency viewership record, which is like massive at that point of time, and we're still growing at that angle. And we also host like bunch of all the sports tournament and matches which India participates in India and across the world. The use case I'm going to talk about is continue watching. I'll give a little background detail on like what continue watching is. Continue watching is nothing but maintaining the state of what the user watches at any point of time, basically. So assume a user X coming to the platform and watches the movie Iron Man with his web or mobile iOS to a Android device. He watches like 20 or 30 minutes on the show in any of the platform, and he says that hey, I prefer to watch more in a Android TV or a Fire Stick TV, such that like my viewing experience can be different. He can just simply switch over from his web or Android devices to the new device. During this transition, he shouldn't be starting from the start of the movie and seeking his bar to 10th minute or 20th minute where he left off and start watching from there. The platform should be intelligently identify that, hey, this guy has watched until 20th minute. I should start from 20th minute onwards in the new device, such that user doesn't have any manual effort or he doesn't have any tiredness of watching any movie. He engages on the platform much more faster, and his experience on watching is like very good for him. That's where the user continue watching comes in, and user shouldn't be searching for the movie also. So whenever he logs into this device, any device, with Hotstar supports in almost like 8 to 10 devices in 10 different platforms basically, and user should be logging into any of the platforms, and he should just see it in on his homepage saying that hey, you have last recently watched these movies like Iron Man or 24 as a show, or these kind of clips you watched. You can start anything you want at any point of time. So the continue watching doesn't limit to just one device. If it is a one device, it'll be very easier for any client to maintain a cache in local, such that they can just start from where they left off. Like I can simply store the Iron Man movie like 10th minute I watched in my local device, and whenever I open the device again, I can start from there. But just to spread across platform also, as I mentioned before, user can watch it any platform, and he should resume from where he left off. And that's where the critical piece of continue watching use case comes into picture, because the Hotstar as a platform has like huge library of content, and user watches across almost like we have 300 million active users, as I mentioned before. User watch like lot of billions of minutes of watch time every day, and we have to maintain those such a huge data in our databases, and that's very consistent across devices, and the latency has to be very small, such that he doesn't feel any difficulty in finding his watch history or where he want to watch it. So it doesn't even limit to only the clips or movies. It also expands to the shows, and shows is where there's a different, altogether different use case, where because assume show AX, I mean, like for example, Agents of Shield, I have like hundreds of episodes in this particular show, and I watched season one, episode two, and I can just simply cut that out, like, and I can busy with my work, and evening, when I come back in the evening, I can start watching it again. In this case, I shouldn't be finding it in the search bar or browse my entire platform to find the Agents of Shield again and find the which episode I last watched. Like I watched season one, episode two. I should start watching from season one, episode three. I shouldn't be searching for it. I should get it on my homepage, such that I can just watch it at the get go. Like I come in, because only time I'm relaxing is I'm watching some movie or something on my platform, and I should be start watching it immediately. I shouldn't be waiting for anything. That's where the next episode comes in. Like we put in the next episode flag in, and the next episode which user supposed to watch it on his homepage, such that he can just start watching from whenever he resume his watching behavior. Another interesting use case is a new episode. Next episode is simpler, because we know that what is the next episode in hand, because the next episode is already available. But what if it is not available immediately? I mean, assume Game of Thrones or any other bigger shows, where the season after season will be resuming after like a year or 2 years after the previous season has ended. So whenever the new season resumes, the newest episode which has been put for the particular show should come in your tray, such that the user shouldn't be searching for the show and finding the newest episode and start watching from there. All the user effort has been cut down, and he just start watching it from the get go on a homepage itself. Before we going into the Scylla architecture, we used couple of DBs before we move to the Scylla. One is Redis and Elasticsearch, and this is how our architecture looks also. This is our client, where user watches their movie or a show or anything, and this just sends a Kafka event, which has been which act as our streaming platform for all the events. We have a processor which reads from the Kafka and then saves the data to Redis and Elasticsearch. Once the data has been saved, our API servers, which just reads from these two DBs and render it back to the client, and that's been shown whenever there's a whenever user supposed to play the movie or play the show, or sees on the homepage where he want to start with. This is a couple of data models we used with Redis and Elasticsearch. For Redis, we just simply used a key value pair kind of a structure, where our user is your key, and a list of content IDs. Content ID is nothing but the list of shows or clips or movies he watched during his last watch, basically. And we maintain this history for long. And Elasticsearch is nothing but a document where key is our user ID and content ID. This is like a per content level information will be stored for like every users whichever content he watched, like movie X he watched, there'll be a document for that movie X with the content user ID as a key. And we have a list of other informations, like what is the movie is about, what kind of language is being played, how much has been played for that particular movie, and so on. In this two DBs, we face list of challenges also. I mean, first thing is like we are using two different databases, and when we have two different databases, our maintenance is completely different also. Because we need to maintain two different code bases, we have to maintain two different query patterns also, and again we have to maintain what kind of latencies we want to get with two different databases. So maintenance was huge, and was like more, which was giving more problems for us. Next is the data size increase. I mean, every 6 months or 1 year or on, we were almost getting double of our data. And whenever we get a double of data, we have to increase our size of our cluster I mean, we have to double our cluster size also. Like Redis, we have to increase by horizontally increase and vertically increase our cluster size. Elasticsearch, we have to increase by number of nodes. And to some extent, this was affecting our cost also, because every 6 months or 12 months, if you are increasing the cost, then it is on use cases not fitting the budget. Next, I'm going to talk about the data model, which we are started using in Scylla Cloud. We maintain the same data structure as the Redis. We maintain the user ID as a primary key and list of container IDs to render the tray at the homepage. And for the second use case where we want to maintain the user and content level information, we flatten the JSON structure into a table where we maintain the user ID and content ID as our composite keys, and we have our timestamp as or when the user has watched this particular content, and other meta informations like languages or country or any other information that's required for our use case. We also analyze few possible candidates before we move to Scylla, like Cassandra, HBase, DynamoDB, and Scylla. We did like a bunch of stress tests and regression tests on top of this, all the databases, and also we consider the cost involved in doing the migration as well as like maintenance across all the databases. And we found out Scylla fits our bill, like it fits our latency requirement and the timeout requirement and other factors which we wanted with our use case. And basically, we felt like two main reasons we went for Scylla. One is the less cost for writes, given we have proficient correctly for our use case. I mean, we didn't over proficient or nodes for a use case or under proficient for a use case. And also our latencies were very low. I mean, you can see in the screen that the 99th percentile of latency is like under 1 ms for write and under 2 ms for a read, which is like very less, and as well as it fits our use case perfectly fine. As I was saying in the previous slides, we sometimes we host a 25 million concurrent users at one point of time, and our DB has to scale enough such that it performs at the same level also. We did a stress testing, and we hit like 10k RPS per node on the Scylla Cloud, on Scylla open source clusters also, and we checked that it's able to handle the load as well as the latencies were under control, and users never even got any errors at their end. Now I'm going to talk about like how we move to migrating to Scylla. I mean, before we were in Scylla, as I said, like we had two different databases, Redis and Elasticsearch. Now we have to migrate those huge data into the Scylla Cloud. Also, in the intermediate, before we migrate to Scylla Cloud, we also use Scylla open source for a few months for our for verification and for our regression and testing and everything before move to Scylla Cloud. So I'm going to talk about all these three migration steps. Let me start with the Redis to ScyllaDB migration. Redis to ScyllaDB migration from Redis, we'll extract the Redis snapshot as an RDB file. There's like inbuilt command for our Redis is there to convert Redis entire data into a RDB file. Once RDB file is generated, you can convert this into a CSV file using an RDB to CSV inbuilt library, which can allow to convert all the data into a CSV format. Post that, we ran a SQL command on independent machine, which can just simply copy the CSV file to the Scylla Cloud destination cluster. The one key thing to notice in this entire process is your Scylla Cloud load realization should be at 100% always. As at the same time, your write timeouts, you should be very mindful about write timeouts, because if you see even a 1 or 2 write timeouts, you may end up in losing a lot of data because you are migrating almost like TBs of data at any point of time. And if you are seeing write timeouts, then you have to find the data which has been missed and you have to rebuild it again. It's like a huge step for you. So you have to be very mindful of that. And controlling the speed of your SQL copy command, you have to be mindful about the threads. I mean, number of threads you supply for this entire copy command. You shouldn't go bigger such that the write timeouts are allowed, and it should be a very less such that the load utilization is below 100%. You should be take the conscious decision on how many number of threads you require to copy the CSV file to Scylla Cloud. Next time I want to talk about like how we cut over from our older architecture to the newer architecture. This is our existing architecture where a processor were writing to Redis and Elasticsearch in parallel, and our API servers were reading from both the different databases, and we're just serving back to the client. Once our Scylla Cloud is up and running and with all the 100% data has been migrated from these two databases to Scylla Cloud, we want to cut over this older databases such that cut over this older databases. For that, what we did is we started writing in parallel to Scylla Cloud along with the other two databases such that we won't miss any data during our migration of our use cases. Post this, we start API servers to read from the Scylla Cloud also at the same time. Once all the data has been completely migrated and we were we are 100% sure that there is no data loss is involved and APIs are also able to read from Scylla Cloud, we just simply cut over from the other two databases. Now there's only one single flow exists where processor just write to Scylla Cloud and API server just read from Scylla Cloud and renders back to the client. Now I'm going to talk about the how we migrated our data from Scylla open source to Scylla Cloud. We performed two different migrations. I mean, two different tools we used during our migrations. One is our SS table loader, and another is a Spark migrator. Let's begin with the SS table loader based migration. SS table loader migration is an inbuilt Scylla tool which helps in migrating the data from a Scylla open source to Scylla cloud cluster. Uh, these are the nodes. These are the three nodes in Scylla open source cluster. There can be like any number of nodes here. From each node of the Scylla open source cluster, run a node tool command to extract a snapshot. Once a snapshot has been generated, you just simply run the SSTable loader command to copy these snapshots to the Scylla cloud. This is like a straightforward and easier way to do it since SSTable loader is like inbuilt tool of Scylla, as well as you are migrating from a Scylla to Scylla. So your data loss will be like very minimal or absolutely zero, and you'll be doing much more faster also, and your data loss will be very less. Another key thing to notice is like I have shown you only three nodes when migrating to the Scylla cloud. This can be increased to any number of nodes in your cluster, but we have to be mindful of the right time modes at your destination cluster such that you won't see any data loss. You can increase the number of nodes, number of nodes to parallel to move more data at in parallel. Key thing which noticed in the SSW loader migration is our second use case where our keys are composite. There the migration is very slow. We expected the migration to happen within a day, but it was taking more than days, and it was not completing really faster enough. So in that case, we synced up again with Scylla team, and we got the idea of doing this Spark migration. Spark migration is it's like a typical Spark program kind of a structure. I'll explain the step-by-step process of like how we did. From the older Scylla open source cluster, from each node, we take the backup Scylla backups and move to the S3. I mean, each node of the Scylla open source cluster, we have to extract the backup, and each of them should be moved to a cloud source provider, S3 or anything which you prefer to work with. Once the backup has been uploaded in S3, you should need to create a new Scylla open source cluster. And once the Scylla open source cluster has to be big enough such that it has to accommodate all the data of your open source cluster. And once the open source cluster is created, we just restore all the backups of all the nodes which we have pushed to the S3 into the new Scylla open source cluster. Once the new cluster has been ready, up and running, and able to serve the request, we start running a Spark migrator code in your EMR or any of your Hadoop machines, and it just start reading from your open source cluster and write it to the Scylla cloud. The key thing to notice in this entire process is, without the Spark, we can run away with like a lot of executors applying, and we can run a lot of tasks in parallel. But we have to mindful that the Scylla cloud doesn't involve any timeouts or any node going down, because if there's any timeouts or any unwanted issues happens because of your increase in load, you may end up in data loss, and you may need to redo every step again and again, and that's not a good idea to do when you do a migration start process. Recently, Scylla has introduced a new tool called Restore. This tool will help in avoiding all these setups manually. You can just simply give your open source cluster, the current production one and the new cluster which you want to develop, and it just your this tool will create everything on hand, and your Spark migrator just simply read from this new open source cluster and just writes back to Scylla Cloud. Few recommendations in my few recommendations we observed during our migration strategy is, as I was repeatedly saying in my other slides also, you should make sure that there is no timeouts. Right timeout should be there, such that your 100% data migration is achieved, and there will be no data loss you can incur on it. And also, in the previous Spark migration steps, always create a new cluster instead of churning from the production cluster which is you want to migrate from, because your Spark can go very fast and can affect your current production system, and it can impact your current production use cases, like all the APIs may latent, or your node may go down. So you have to be mindful of that. So always create a new cluster and try to migrate from there. It'll be much more faster and much more simpler for that. We have other future plans also for Scylla Cloud. Currently, we have like only a couple of use cases for Scylla Cloud. We are thinking of moving more to the Scylla Cloud. For example, watch list. Watch list is nothing but a bucket where we put in. User can put in all his whatever the watch later kind of things. Like I want to watch Terminator in and later point of time, I can simply put in watch list, and I can come back and watch at any point of time as a reminder for me. Also, we as a streaming service, we store all the recommendations data which we use for our offline recommendations, like hey, this guy's watched X show, I can provide more recommendation along with this particular show. I can store them also. That's all from me on the Scylla migration and first use case. I'm handing over to Vamsi for the second use case. Thanks everyone.
Hello all. Hi, I am Vamsi. I work with Bala in Hotstar. Today I'll be covering about user watch store. This is our second use case which we use Scylla for. If you see this screen which is shared, you'll find that when you watch in Hotstar a movie or a TV show episode, recently you will see a tray called because you watched with the show name or the movie name. Like for example, if you watched MasterChef Australia, you may get more recommendations tray for this on the homepage. So user watch store is what is one of the infra underneath it, which powers this kind of use cases. So like how does a user watch store work? User watch store is comprised of like two tables, where one table has the raw user events and the second table has the aggregated events. So once the users like event comes for any activity user has done in the app or in the website, the raw events are actually coming via Kafka. They come via Kafka and then actually get stored in a raw table. And the raw table, there's a job which runs on the raw table, takes the data, aggregates them, and then writes to the second table. This is one of the use cases which Scylla was used for initially. Here, the data is, the main table has data in the time series format, and it's all append only on the main table for the writes. And the reads, when they actually happen, collect the data via range query and then take the data from the main table and write it to the new table. And there's one operation also on top of the main table, which is expiration, after which it will delete the data from the main table. The mutations on the main table primarily are inserts and deletes. Now, if you take the use cases is like we can query on the aggregated data, which will be more of the aggregations. And if you want some raw, like last 5 events of a user action, those kind of things will actually be queried on the main table. And this has a very high scale, like whenever there is an event happening or whenever there is a lot of people watching a recently launched movie. There are some multiplex popular movies which get launched even during those time or during the event like IPL, where a lot of people will come and watch cricket or World Cup. So there'll be a lot of volume coming to the system where there are lots of writes. So this user store has to support both of them. So we noticed that when we initially used the Scylla open source and then deployed in-house, it ran fine until then. The version which we had at the time was older, so it ran into issues with whenever there's compaction which got triggered, we ran into issues where the node used to like error out, and then there used to be a lot of lag, and the latencies used to like go to like 10 seconds for P95 and both read and write. This was this is actually an outage for us, where something like the picture which I showed you before cannot be powered anymore for the user, and it was disabled. So how did we when we tried debugging that, we noticed that our use case of deleting a lot from the main table, that too very frequently, is an anti-pattern. So what is an anti-pattern here? Like if you take one table, the example here is like there's a table called queues, and there are lots of entries in the table. And if let's say we are deleting it, what happens inside Scylla is the delete will be marked with a tombstone, and the compaction process happens underneath, and then tries to reclaim that and then save space. So the compaction process is essentially because there's a mem table where the data gets written first in memory, and then once the mem table reaches specific size, it gets flushed to the disk where there'll be SS table created, and there'll be multiple such SS tables. And depending on the compaction strategy, here it is like size tier based compaction. So once it reaches specific size, it will be compacted into a bigger SS table. Even there, like once it's actually reaches one specific size, it will be like compacted into even bigger table. That is how usually compaction works. And during the process of compaction, if there's any tombstone which already got created, they'll be claimed. So that is how we actually recover space. And when there is, and also when there are lots of records with tombstones, whenever the scan happens, it has to like not consider that records. So there is some penalty with having tombstones. So we noticed that the reason for our open source cluster going down is like there are like 3-4 reasons which contributed to it. We'll cover how did we attempt to discover that and how to solve that. So one thing we noticed is like the Scylla client has a consistency level for any operation which you can do, and the operation for deletes when we do like we didn't set the consistency level to all. When the consistency level is not all, or like if it's one or like a quorum or local quorum, not every node will do the delete at the same time, because of which like there is repairs. Like when the repair actually happens, there's a lot of activity which is happening. So one thing which we tried was to try CL equals to all for deletes. That kind of reduce our assumption was that it will reduce the repairs, and hence the read latencies will improve. So other thing which we tried was especially during an IPL match, or like whenever the match which is happening for a limited time period, we would not like any compactions, any heavy compactions to be running during that time. So the idea was that we will not we'll run one major compaction every day during off-peak hours. When we ran that major compaction, it'll try to get that single SS table created for the tables, and it'll actually be easy to query, and it'll be fast, and latencies will be less. So when we tried that, we actually during the match time, when we wanted to improve the latencies, we were seeing the improvement in latencies, and they are back to normal. There are spikes, but they're like good enough later. So that is our use case. So in general, our learnings are like whenever you are having lots of deletes, that's not ideally a good pattern for like this big table kind of systems where there are when there is like SS tables created, and like the tombstones have to be reclaimed. For those kind of use cases, don't delete often. Or if you're doing like if there is unavoidable, you have to like try with different compaction strategies. Or if you want, like one question which we were asking Scylla team was like, can we like in HBase we can disable compaction and then do one compaction towards the end of the day. That kind of system we can that kind of a configuration we can go with, so that the frequent compactions won't affect your performance. We'll go for Q&A.
That's great. I want to thank Bala and Vamsi for a great session there. We're going to start the Q&A session in just a second, but before we do, we've got another quick question for the audience. So we'll start a second poll question here. And as you saw, Disney plus Hotstar has just massive workloads. We want to know how much data you have under management in your operational database system. Is it less than a terabyte? Is it 1 to 50 terabytes, 51 to 100 terabytes, or more than 100 terabytes? We'll spend just a couple more seconds here with the poll. Please give us your feedback. Again, we'll share the answers with all the attendees today with the link to the recording and a PDF of the slides. And let's go ahead and close the poll. Thank you for that. And now let's start the Q&A session. And I'll remind you that we have both Bala and Vamsi to answer your questions. We've gotten a lot of questions so far. And we also have Adar, who heads up the product team responsible for Scylla Cloud. So if you have Scylla Cloud specific questions, you can ask those of Adar as well. And I'll dive into the questions, and I'll let you guys decide who's going to answer which one. We got a lot here already. So we got a variety of different questions, some more technical, some on pricing. I'll start with this one. What does low latency mean in ScyllaDB? That might be a question for Vamsi and Bala. You could share your experiences there.
I can take it. Like in our case of continue watching, we noticed that the lesser the latency, the actual user experience is better, because finally, when the client actually makes a call, the network coverage may not be good for the end user. So even a slight increase in milliseconds at the backend can be a bigger time period for the user. So once we switch to Scylla, like we noticed that they are like sub 5 ms, like sub 10 ms millisecond latencies for reads, because our reads are like pointed reads. They're not like in the second use case where they are like kind of batch and like range based. If it's like a pointed read, latencies are actually good in the order of like less than 10 ms.
That's great. Thanks for that, Vamsi. Adar, anything you want to add?
No, thank you, Vamsi. That was great.
It's a good answer. Here's the next question. This is from a Scylla user we know, Keith Sater. Keith, thanks for this. What was the criteria the team used to pick the replication factor? Bala or Vamsi, either one of you could answer that.
Bala, you want to take it?
Yeah, so we picked the replication factor based on our data, structure. We kept as 3 to be. That's the standard, right? Consistently we want to use that. That's recommended also. We didn't actually put in any big factors into it. We just want to maintain such that it's spread across all the data zones, availability zones. We use AWS as our cloud descriptor. Cloud manager. So we want to make sure that the nodes are available in all the zones, and we won't lose any data. Even 2 of the availability zones are like gone down or something like that. So that's a key factor which we looked into. That's it.
Thanks for that, Bala. Here's another question. What things do we need to keep in mind if we wanted to delete data from the table we are using TTLs?
I can take it. So the deletes, if in the second use case, we can either set a TTL there, or you can actually do a delete using the client. So you are doing deletes using the client. That's where our CL equals to all helps there.
Great. This is a longer question I'll ask. It says, one generic question. Every minute, are we storing the watch timestamp in a particular chosen movie for suggesting continue watch from where we left, or while closing/choosing pause to interchange from mobile to TV or vice versa? Did that make sense?
Yeah, so we kind of do both. We store when the user makes some action, as well as we do it in the background also. Our client is intelligent enough to send the bulk of events in the background, and we process them at rate of whenever it receives it at the backend. Yeah.
Great. Here's one about your migration to Scylla Cloud. It says, Bala, you mentioned during your transition from Redis and Elasticsearch to open source Scylla and to Scylla Cloud that you noticed increased latency when copying data with a clustered key. Can you talk about that a bit more? Was it because of your data or something else?
Yeah, so as in the second table which we had, where we had two different two keys. I mean, one is the primary and secondary key we had. During that time, we ran the table loader migrator, but because of the creations of new what do you call it, tombstones and other partitions and everything in the new destination cluster, table migrator was latent at that point. So it was very slow. I mean, the other table which we had like one primary key alone, the data was migrated within like we migrated almost like half of a TB of data within 6 to 8 hours period of time. But it was not the case with the second use case, and we spent like almost like 2 3 days was running the same command, but nothing was moving much faster. That's when we switched to the Spark migrator. We thought like the data migration will be much more faster. Yeah, that's when we moved to the Spark migrator.
Thanks for that, Bala. We've got a comparative question here. What is the main difference compared to Cassandra regarding Scylla? Adar, that might be one for you.
Can you hear me? Yeah, sorry.
Yeah, we hear you. That's right.
I mean, I can recite the obvious things, but I'm interested to hear Vamsi and Balak, your point of view on that.
I'm sorry, I don't have much experience on Cassandra. Vamsi, you want to take it? Yeah.
Yeah, one thing we have noticed like is the efficiency of the number of CPU cycles taken to like for rewrite operations when self-hosted is actually cheaper with Scylla. That was though like this is like when we did the analysis like around 2 years back.
Yeah, and to add to that, we have performance testing showing that latency and performance for Scylla is better.
Yeah, and I'll point anyone that has that question to our website as well, because we do cover it quite extensively there. Here's more of a migration question again. How much downtime was required during the migration and cutover?
Absolutely zero, actually. I mean, user didn't even realize that the data has been migrated. There was no downtime, and I mean, we didn't. I mean, it was not like we ran it like nights or off traffic hours to avoid the downtime. We ran it in during the live event. I mean, live traffic also. But user never felt any downtime at any point of time because of our cutover strategy, which I mentioned in the slide also in my presentation. I mean, we tested with like, I mean, we have done like migration in the past, and I mean, with the experience, we got better, and because of that, there was no migration downtime at all.
That's great. We've got a question about latencies. Siddharth asks, can you share your latency requirements?
I think we already shared that like we wanted like less than 10 ms latencies for reads for continue watching. And for the other use case, we are still tuning the latencies. We would like to have like, because they're all user facing calls, any call which is made from the client, we have a target to keep it in like at max tens of milliseconds, not more than that.
Thank you for that. Here's a high availability question. Could you please elaborate on the HA and DR of your cluster?
These for the pre-Scylla Cloud or during the Scylla Cloud?
You know that he wasn't specific in the question.
So with the Scylla Cloud, with our replication factor and availability zones, that'll handle the HA for us. And Scylla Cloud is managed by the Scylla team. In the previously when we were self-hosting it, we took care of the same topology for deployment. Within the same, like we still done in one data center only. We don't do cross data center yet.
Here's a specific question. We have a use Spark batch job to push 80 gigabytes of data to ScyllaDB. How will it perform in this case? That might be one for you, Adar.
Yeah, I'm trying the performance what, of pushing the data? I'm not sure I follow the question, I'm sorry.
Yeah, that's from Kanwar. Kanwar will ask you for a kind of a more specific question there. Here's another one. Why were SQL databases not considered for the first use case? That's for you, Bala.
Basically, the data size we have is very huge. I mean, we had in the orders of TBs, and also we wanted, it's a very big data. So distributed databases what our first choice was. I mean, current MySQL or any SQL databases won't easily fit to it. Also, our latency requirements were very critical over there. I mean, as Vamsi said, like we are under 10 ms was the latency requirement for us. So SQL databases we tried to start with, but it didn't fit our use cases. That's why we didn't go for that.
That's great. Here's a cache question from Benjamin. Is another cache being utilized to cache reads, or do your API servers hit Scylla directly?
Our APIs hit the Scylla directly. Currently we don't have any cache in front. Previously, the Redis, which I mentioned, that was the cache which we used for previous architecture. But currently, everything's been hitting Scylla Cloud directly. No cache involved.
That's great. Question from Sriram. What considerations did you have to make for choosing your primary key and clustering key?
It depends on the use case. Primarily, I mean, for our use case, we required two keys to be primary and secondary key. And as we see, like we have two different tables, right? One of the table doesn't require it. One of the table just want to identify by the user. So we didn't require to keep another key as a secondary key or something like that. So that's why we just had only one primary key. In the second use case, we wanted to search by user and by content. That's why we had like composite keys at that point of time. Yeah, it depends on your use case.
Great. It's a very specific question. While migrating from Redis to Scylla, taking an RDB snapshot, converting to CSV, and loading into Scylla, during this time, more data is coming into the system. How did the loading of old data and the new incoming data, how was that kept consistent without the downtime?
So before we started the migration, right? So I'll just go on the step again. So once I got the CSV file, our Scylla Cloud is generated. I mean, Scylla Cloud is created. It will be empty completely. I mean, it's just a table will be created with the empty state. There will be no data present in the newer cluster also. So now we copy the new CSV file to that. And as we mentioned in the presentation also, like we use Kafka for our use cases end to end. So we just simply reset the processing offset to earlier point of time, like maybe a week or 10 days before that, at the point when the CSV has been generated. And we just simply redo it from that point of time, such that our processing will be start from that, and we don't lose any data in between that. Yeah, I mean, I guess I answered the question. I mean, we parallel write at that point to all the three different sources, such that no data loss has been occurred at that point.
Thank you for that, Bala. Here's another question around Elasticsearch. What and why did you keep an Elasticsearch cluster that you moved to a Scylla cluster? These DBMSs are intended for different purposes, and I wonder how these could be interchangeable.
So Elasticsearch didn't fit our use case, to be honest, to start with. I mean, we started with Elasticsearch assuming that it may fit it, but later point of time, we realized that Elasticsearch is not a perfect data store for our use case. Yes, I mean, SQLs would have been the first thing to start with, but I mean, previously because we were not aware of a lot of other DBs, we started Elasticsearch with our knowledge. Later on, when we found that Elasticsearch was not the right data store, we look for other DBs, and that's when we moved to Scylla.
That's great. I'll ask a question. This one was actually submitted by email from somebody who registered about a week ago. With all the data being ingested into Scylla, how does that data bubble up into detailed line item reporting, analysis, and summary visualizations to improve business operations and extend the Scylla ROI?
Vamsi, you want to take it?
Like in our case, we don't use it for reporting. So I didn't fully understand the question.
Shall I repeat it?
Yeah.
With all the data being ingested into Scylla, how does that data bubble up into detailed line item reporting, analysis, and summary visualizations to improve business operations?
Is it about the with respect to business metrics? What we measure is are users able to interact well with the app or not? That means whether the continue watching is working correctly or not. So that we can measure those, but I didn't fully understand. We are not using it for any reporting purposes currently.
Okay, fair enough. Here's another comparative question. We had one about Cassandra earlier. This one is, what is the cost difference between DynamoDB versus ScyllaDB in this use case? Is that something that you guys looked at?
Yeah, at that
No.
for the continue watching use case, for the writes, there are lots of writes. So writes was evaluated, and for the reads, DynamoDB has this DAX. DAX actually, if you go through DAX, you may actually get much cheaper reads if reads are the only thing.
Here's another question. How do you avoid performance degradation in the case of deletions?
So that is essentially the second part of the talk. So we were in our case, the deletes are like batch deletes. There are lots of deletes. When the deletes actually happen, the compaction has to reclaim the tombstones. So that we have to manage it carefully depending on the kinds of deletes. If they're very less deletes over the let's say every X minutes there is one or two deletes happening, then it's not I don't think it will be that big of an issue. But when the deletes are when you're deleting thousands of records or tens of thousands of records in seconds or less than a minute intervals, then that is where we are actually facing the issue. We were facing the issue, and we took some kind of actions, and we are still tuning it.
Here's another question from Siddharth. Without time factor in the primary key, don't we run into ever-growing partition sizes?
In our case, the key is distinct enough. It will be distributed well enough without any skew.
We've got a number of questions asking where the video streaming is actually stored. Are you also using Scylla on the video streaming side of Disney Plus?
No, we don't. We don't use any videos in Scylla.
Okay, great. Yeah, that question was asked a few times. Let me see, here's another question. You talked about expiration on the user watching. How far back do you keep their history? Are you using TTLs or other data eviction? I think you actually addressed that during the talk.
Yeah, there's a time period after which it will get deleted. It will get aggregated and deleted.
We just got another question here. Do you run any analytics on Scylla, like which action movies are in the wish list, or do you also load the data somewhere else for analytics?
Currently, we don't, but we have future plans to use it the same.
Right. And another one. What language do you use to save data on the database? Do you use containers to scale the application?
We use a Golang application and we run on Kubernetes.
Kubernetes, okay. Okay, why don't we wrap up? We'll just have one more question here. Let's see if I can pick the right one. Find there's a few that are just kind of repeated here. Oh, I'll ask this one. Is the search also powered by Scylla? I think you did address that.
It is not.
Yeah, and again, we've got a lot of people asking the same sorts of questions, so I was trying to group those. I think that's it. We'll give a last chance for people to ask questions while we still have you. Here's one.
Bob, there's one question of why are there two tables required for continue watching use case? Yeah, we can club those two into one table. That was due to legacy reasons. We can actually club those two tables into one table. Sorry.
Okay, great. Thank you for that. And then we got another one that just came in. Can we have used Redis to serve the same purpose instead of using Scylla?
We have, but problem with the Redis was ever-growing data, and as I mentioned in the presentation also, we needed to scale our cluster every 6 months to 12 months period of time, and it was not. It was not feasible for us, and it required all the manual effort to do that. That's in order to avoid this and also avoid the reduce our cost. We moved to Scylla Cloud.
That's great. We've got a number of other questions in, but they're sort of redundant with questions that were submitted. So I'll tell our audience, first of all, thank you for submitting so many great questions. If there's anything that was left unanswered, we'll follow up afterwards and make sure we get answers to you. And I want to take the opportunity to, again, thank Bala and Vamsi for your time today. Thanks, Adar, for joining us as well. We much appreciate your time and thank you for this. And for our audience, we'll follow up again with a recording of the webinar, the answers to the poll questions, and a PDF of the slides themselves. So thank you everyone for joining us today.
Thank you.